Looking at this next example, we can see here that we have a compressed spring and there's a 20 kilogram ball that's placed next to that compressed spring. That all happens to be located 15 meters above the lowest elevation point. The ball will be launched, it will roll down this hill, slide across where A is located, go back up a ramp, and then it will hit this frictional section. This frictional section exerts 12 newtons of force on this ball. And what we'd like to know essentially is A, how fast is the object traveling at A? And B, how far on to this frictional section will the object travel before it actually comes to rest? Because as it slides across there, friction is going to perform work, and friction is going to take some of that energy away. I want to know, after all the possible energy has been taken away that friction is capable of removing, how far onto that surface will this object have slid? Now, that's also what's known as stopping distance, like when you're driving your car and you slam on your brakes. How far will it go before essentially all of the kinetic energy of your car has been dissipated into heat or sound or something that's no longer usable for motion or changing your position? So let's start with finding the velocity at A. I won't spend too much time on this because if you notice that from my starting point to point A, there is no friction, there are no outside forces, that tells you that there's no work being performed from the start to point A. So I have a much simpler calculation. So as I said, there's no work between these two locations, so I quite simply just take my normal equation. Gravitational potential, kinetic, and elastic potential added up on both sides, or at the start and at point A, must be the same value because no work occurred. Well, I don't have any velocity at the top, so I have no kinetic, and I don't have any height or spring compression at point A, so that only leaves me with the height or the gravitational potential at the top, plus the spring, or the energy stored in the spring at the top, and by the time I reach the bottom, it's all just kinetic. If I plug in the equations I have, my gravitational potential plus my elastic potential at the top equals my kinetic energy at point A. Plugging in everything that's known, we have the mass, gravitational acceleration on Earth, and the height of 15. 1/2 the K value of 800 times the compression, which is 0.6 squared, must equal half the mass times the velocity squared. Plugging that all in correctly, I should find that that object travels at 17.57 meters per second. The trickier part comes here, determining the stopping distance. But again, it's no different than the previous examples in terms of how we solve it. My locations, again, will be my starting location and point B, which is at some future distance from this point right here. Now, if we recognize the fact that between the start and B, there exists some frictional forces or some outside forces that will take energy away, that lets us know that there is absolutely work performed from start to point B. At some point along the way, granted after point A, but at some point along the way, work is performed. So that just means I will list out my normal equation, adding work to the starting side because I need to account for the fact that the energy I started with plus the work that was performed on the way to B must equal whatever is left at B. There's no motion when the ball is at the top, but it does have height and spring compression, so that leaves me with these two at the top, plus the work that's performed at the frictional section. The only thing that's left when this object comes to rest is the energy associated with its height. It loses all of its kinetic. It does not lose this potential because it still has 7 meters of height at the end. So what that tells me is my starting height plus the energy in the spring at the beginning plus whatever work occurs must equal whatever remaining gravitational potential energy I have at the end due to that 7 meters of height. Again, I just substitute everything that I have, knowing that work is accounted for by multiplying the force that's acting against the object over a given displacement times the cosine of the angle between them. And on the other side, I just have my GPE. So if I plug in everything that's given to me, and I account for the fact that I have 12 newtons of friction acting over some unknown distance, and that the angle between those two is 180 because the object slides right while the friction acts left, and that's a 180-degree angle. If I set all of that equal to the mass times 9.81 times the 7 meters of height that I still have at the very end of the problem, you hopefully notice I have one equation, and the only unknown is how far that object must have moved when it was on the frictional section. If I very carefully calculate that, and I've done my algebra correctly, I should find that that object has traveled a distance of 142.8 meters. That is the only distance that it could have traveled in which all of the kinetic energy would have been converted out of the system to heat or sound by friction, and I would have been left with only whatever is remaining as my gravitational potential energy at that final location.